have a fairly thin attendance today. Not entirely sure why. Maybe we might want to ask in the group. Okay, so we did have a case presentation which was to be done by Ruchi and Neeraj. And given that we don't seem to be able to find either of them, we will go ahead and go straight into the part which Bhama will be covering, which is tessellation. Then that will be followed by Sendil. So Sendil, would you need any material for people to be having?
Definitely 4 sheets, a scale, and maybe a sketch or a pencil. That should be a color pencil, something like that. 4 sheets for sure. 4 A4 sheets.
Yeah,
definitely.
So if you can keep a few A4 sheets ready with you and probably a scale and a pencil, I mean, all of that should be pretty handy. If you can keep that ready for Sendil sessions, we will need some live demo is what Sendil will be doing. And finally, we'll just wrap it up, take a feedback, if any, and then move on. Yeah. Okay. I will now hand over to Bhama. Yes, audio.
Yeah. Thank you, Ramesh. So today's topic is something different, what we don't usually find in our textbooks, but this can be very nice. In this, we can do very nice activities for children when we are teaching them 2D geometry, and it's very enjoyable, and they can do very nice projects in this. So it's totally beautiful, as I will try to. Yeah. So let's start. So what are tessellations? Tessellations, like we see tessellations all around us in real life, like in the flooring and the tiling patterns in the bathrooms and kitchens. And so what exactly is a tessellation? A tessellation, these are patterns that are made up of repeating shapes. And secondly, there are no gaps or overlaps in the patterns. And third condition is they can go on forever in a plane. So that's what we mean by a tessellation. So now just let us look at the simplest of tessellations possible, made up of regular polygons. So regular means all sides and all angles of the polygons are equal. Our equilateral triangle is the simplest polygon, 3 equal sides, 3 equal angles, and they can tessellate as shown on the left, right? And then we have the square, and that also tessellates. So there are no overlaps, it just fits in perfectly on a 2D surface. And then we have 6-sided regular hexagons. They also tessellate. And these we have seen, they are very popular, and we have seen they are very common too. So now let's look at a pentagon, right? Can a pentagon tessellate? So suppose we try to arrange 3 regular same-sized pentagons to meet at a point as shown, right? Then we have a gap as shown in brown, right? So why do we have this gap? So if you look at the regular pentagon's interior angle, it's 108 degrees. So 3 times that is 324, and which is less than 360 degrees, and that's what we'll need if we don't want a gap. And if I keep a 4th pentagon, that's also not okay, because it starts to overlap, because 4 times 108 is 430 to 100 into 432, and so this is greater than your 360 degrees. So now we get this idea, right? So why do some regular polygons tessellate and some don't? So this question, it has to be asked to the children when they are studying polygons, and they can the hint is to think in terms of interior angles if you want to give them a hint, or just see if they can find it out on their own. So the answer is pretty simple. So at every vertex where the polygons meet, the interior angle should add up to 360, and then so that the polygons don't overlap, right, or have any gaps. And so for a single regular polygon to tessellate, the interior angle should be a divisor of 360. Correct. So now if you look at equilateral triangles, we see 6 of them, they meet at a point. So why 6 of them meet? Because 360 divided by 60 is 6. So I have marked these red dots. Okay, if you concentrate on the red dot, we see that 6 triangles meet at that point, 4 squares meet, and only 3 hexagons meet. Why? Once again, if you divide 360 by the interior angle, it gives us directly the number of polygons that meet. And certain polygons, they don't divide 360. The interior angles, they don't divide 360, right? And so a tessellation formed just using these kind of regular polygons is called a regular tessellation. So now we come to more than one regular polygon, and these are called semi-regular tessellations. And so now if you look at tessellations formed by 2 or more convex regular polygons. Okay, and so once again, and these are sometimes called Archimedean tessellations also, and there are only 8 such tessellations. So these can again be discovered by the children, and of course, one point I forgot to miss: the sides of these regular polygons should be the same size, right? Each side should be the same length, otherwise they won't fit together. So let's look at a little bit more detail at each of these. Yeah. So now if you look at the first figure over there, and then once again I have a red dot marked. So if you look at that, concentrate on that red dot, what do we see? We see that it has one square, one octagon, 2 octagons together around that one red dot. Okay, so the polygons at every vertex, okay, in this kind of tessellation, at every vertex, we call it as a vertex configuration, is 488, where 4 stands for the square, 4 sides, octagon is 8, and once again an octagon, and we denote it by 488. And if you look at the interior angle sum, the sum is going to add up to 360. 90 plus 135 for octagon, and 2 times 135, so they add up to 360. Again, the second one, so at every vertex, right, you look at the red dot, we see a square, a hexagon, and a dodecagon meeting, 12-sided figure. So once again, this is denoted by, this tessellation is called 4, 6, 12. And the angles, interior angle sum adds up to 360. Similarly, the next one where a triangle and 2 dodecagons meet, and once again the interior angle sum adds up to 360. So we can ask the children, give them many regular shapes and ask them which tessellate, and they will find this out quite easily.
Okay. There's a curious pattern one can see here.
Yeah.
If I take 488 and add up 1 by 4, 1 by 8, and 1 by 8, it's half. And then I do 1 by 4 plus 1 by 6 plus 1 by 12 is half. 1 by 3 plus 1 by 12 plus 1 by 12 is,
that is nice. Yeah.
Yeah,
Nice.
it kind of flows from the 360 divided by 1 minus n, that kind of a thing. I don't know. Yeah.
Okay, I should think about it. But what if more than 3, even that? The next slide, please, Ramesh. We'll check that.
Yeah.
The next one. Here you have, so we have 4. Even here, is it 1 by 3 plus 1 by 4? Or maybe.
No, it crosses it.
It crosses it. Okay.
Yeah.
Okay. Yeah. So this figure on, so for 3 polygons meeting at a vertex, it comes to half, is it? Okay.
Yeah, this comes to 1, by the way.
It comes to 1.
Yeah.
Okay.
Yeah.
Yeah, so the figure on the left, it's in Spain, in a museum in Seville in Spain, and the same pattern, you can see there's a flooring over there, and this I've tried to make on the right at home, and the vertex configuration of this is 3, 4, 6, 4, which means a triangle, a square, a hexagon, and another square. They meet at a point. So it's and in that order, the order is also important, as we'll see in the next figure. So over here, both of these, okay, tessellations have 3 triangles and 2 squares meeting at a point. The order is different. So we have 2 triangles and a square, a triangle and a square in the first one, and the second one we have 3 triangles and 2 squares, and both form completely different patterns, as you can see. So the order in which we put these polygons together also matters. And so this is one last tiling pattern that I've tried to put with a couple of hexagons and 2 triangles. And so what we have seen till now is semi-regular tessellations are made with 2 or more regular polygons having the same side lengths. And all these can be done as nice activities for kids. So now let's look at tessellations that use more than mere polygons as tiles. And this beautiful tessellation of birds, it has a rotational symmetry, a 4-fold, right? And why 4? Because it was started using a square. It started off with a square, as we'll see. And then we'll see how we can make this in the next few slides too. So this MC Escher, he's quite famous. He's an amazing. He was a graphic artist, and he made beautiful wooden carvings and lithographs. And he had a very strong, all his drawings, his artwork had a very strong math component in it. And he also made these amazing tessellations as shown on the left. No, that he didn't make, that's a tiling. Okay, so on this, in the center and on the right, so this is a picture he has drawn this, okay? It's like an impossible object. If you look close, it's like a series of stairs which keep on ascending or keep on descending. It's called the impossible flight of stairs. It's like an optical illusion. He has just drawn it. You can never make this as a solid piece, right? Something that goes on increasing or something that goes on decreasing, and it meets also. So on the left is this this is called the Alhambra, the site again in Spain, where there's beautiful tessellation. And when traveling, he was very inspired by this architecture, right? And so inspired by this is when he started creating his own artwork, which had these beautiful tessellations. So these are some of his famous tessellations that he created. So he wanted to create tessellations of not just ordinary polygons, but then he used images of animals and birds and people. And how did he do that? He went about it in a very systematic way. He started using rhombuses and squares and parallelograms and equilateral triangles. He took into account the symmetry of these figures. So over on the right, you can see that he started off using equilateral triangles, and then he has he has evolved this to make these beautiful shapes of birds flying out. He could tell like stories, right? So this right side, he named it liberation. That is, from a very rigid mesh of triangles, he had these birds which fly free into the sky. And then in the center, it's like how fish, it evolves into birds flying. And then on the left, we have these horses, these flying horses. So the first two, that is the horses and the thing, he started off with squares, and then on the right, he started off with a triangle. So we'll look at how these can be created now. So on the left, right, I have started with a square, and then what you can do is you start cutting the square. So how do you cut the square? You start at one vertex and end at the adjacent vertex. Okay, and you can make any design. And that cut, what you make, the cut piece, you take it and you attach it at the opposite side. Okay, just slide the piece. Don't flip it or don't rotate it. Okay, and then you tape it, and this is your tessellating style, and it's going to tessellate as shown on the left, right? So in the second set of figures in the center, you see you start off with a hexagon, and then you create this pattern, you cut it out, and then you again rotate it, and then to the next adjacent side. And so we get this family of lizards, which is again Escher's creation. That's how he has created his, because you start off with a hexagon, it has a point rotational, threefold rotational symmetry, 120 degrees, right? And then on the right, you can see how if you start off with a square or with a parallelogram, you can create these tessellations involving horses, flying horses, or barking dogs.
And we can rotate or slide as we wish, is it, Bama?
No. I mean, we'll have to see, like, if in the first one, the first what I've shown, if that one, if you're going to rotate it, right, the way it will tessellate will be different. So some of them will have, so on the left by your translate, so that has translational symmetry. But the same thing, if I rotate it and keep it on the side, it's going to have a rotational symmetry. But then we'll have to see, we'll have to experiment it, I mean, try it out, and then see if we can do. So for example, yeah, the next one, the fish, if I slide it, yeah, the next, yeah. So over here, this one, as we can see, it will have a translation symmetry. So what I have done here is I have taken a square and then embedded a circle inside and just cut these two small pieces shown in dark brown, and then slid them to the opposite two ends, right, as shown by the red arrow. And then you get this fish kind of a tessellating tile. And with this, you can make these drawings and you can color them in any way. And this activity children really enjoy. They love drawing. And the next one, if you can see, the next one is this over here, because it is in this way we can create a rotational symmetry. So when you're moving it to the side, then you have to do it for all the three sides and make sure that you slide it in the same way. You rotate it in the same way, and then we'll get this a kind of rotational symmetry figure, which you can again decorate it whatever it looks like, shells, or maybe I've tried drawing birds, something like that. So these are very nice activities which involve a lot of art and a lot of math, and it really enhances a child's, visual skills, their sense of symmetry, can teach rotational and translation symmetry with them, and polygons too. So now, whatever now from now on, it's about a little recent research in tessellations. And because like I thought, like as teachers, we can enjoy this whatever work has been done. So I'll try to explain to the extent I have understood. So yeah, so now, so till now, the type of tessellations that we have seen is you start with a tile and then you add tiles to it, you spread outwards, correct? You fill up the 2D plane. But another way to define a tessellation is to go from the outside to the inside, where we create more and more details and similar to a fractal construction. And so this is what Sir Roger Penrose did. He took a regular pentagon, he replaced it with 6 smaller pentagons that fit inside, right, as shown on the right top right. And then he added some, like this, he had some 4 substitution rules. So one pentagon can be replaced by 6 smaller pentagons, and then a boat shaped figure can be replaced by 3 pentagons and a star can be replaced by again smaller pentagons and a smaller star inside, and so on. So using these 4 substitution rules, right, and here at the bottom, figure 4, it's just the red part of it marked in maroon is enlarged, and so we are going inside, further and further inside, so it's sort of magnified picture of that. So the tessellation that we create using this is in the next figure, next page. And so this is how every generation evolves when we have these substitution rules. Yes, rangolis will have, the rangolis patterns that we, yes, when we do connecting dots, it is a form of tessellations, definitely. Not the ones which go around the dots, but the ones which we connect dots using straight lines, yes. They are a kind of tessellation, yeah. So yeah. So now this one is an actual floor tiling, and this tessellation, we can see the 4 shapes: the pentagon, okay, the pentagram, which mean the star, the half pentagram, which is like your boat, and then the rhombus. And what is most amazing about this tessellation that Roger Penrose created was that this pattern never repeats. So this is amazing new discovery. So what we mean by this, a pattern never repeats, this is called an aperiodic tiling. Periodic is it repeats, right, over a period, but aperiodic is it's a non-repeating tiling pattern. So yeah. And this, he further refined this, Roger Penrose. So just with 2 tiles, and it is the fat rhombus and a thin rhombus, he succeeded in creating these aperiodic tilings. So this, I mean, it was such a discovery, it was such an amazing thing, because till then people thought if you're going to use regular shapes like a pentagon or what shall I say, a hexagon or whatever the tilings you've seen with any kind of rhombuses or whatever regular shapes, the pattern is going to repeat, right? So it means that suppose I have a tile, I have a square floor made of square tiles. I know that when I walk a little bit across, I come to a square, I know the rest of it is all going to be squares. But over here, how much ever you walk or how much ever you go translate across this 2D surface, right? You go across this 2D tiling, you can never predict what the tiles are going to be. And that means it has no translational symmetry whatsoever. So it goes on and on forever, but then still nothing ever repeats. And that is something which people found totally amazing and really spectacular. And it is just made with 2 very simple tiles. And he made, Penrose made very different versions of this aperiodic tiles. So this is called the kite and the dart. And what is another very nice thing about this is he created these two arcs in red and blue, or light blue, I think it is. So in the middle of these, the kite and the kite and the dart tiles, and he had a rule. So when you place them, the arc should be contiguous. That is, they should form continuous curves. And if you follow this rule, then once again, this styling is aperiodic. And so on the right, you can see all these, the arcs, they form continuous curves. And he also had a set of substitution rules as shown on the top right.
Okay. The darts are to be contiguous, meaning
Not the darts, the arc in the darts.
Okay.
That way, like when we keep the tiles, right, we should keep it in such a way that the arcs, they form a continuous curve.
Okay.
Yeah.
And when you say phi, is it the same phi as what we saw in a couple of
Yeah.
sessions?
Yeah, it is the same phi, that same, the next, I think, the next slide, I talk a little bit more about.
Okay.
Yeah. So this is the intuition behind why these tiles form this infinite non-repeating pattern. And Penrose did this only with pentagons. So with pentagons, we can give this is the intuition behind. So we see that earlier sessions, when we talked about Fibonacci numbers, the pentagon is closely associated with the golden ratio. That is, the ratio of the diagonal to the side of the pentagon is that phi, that is 1.6 whatever. And then since the kite and the dart are actually sections of the pentagon, the kite and the dart have the golden ratio built into the construction. So the ratio of the lengths of the longer side to the shorter side length of the kite and the dart is phi. The ratio of the area of the kite to that of the dart is again phi. And if you take any large tessellating, you tessellate them with these kites and these darts, right? These shapes are called, and then the ratio comes close. The number of kites to the number of darts, it comes again close to this golden ratio. And this golden ratio is an extremely irrational number, like we saw in that. And because of that, they say that the pattern cannot possibly be periodic. So that's the part of the evidence that shows that the pattern cannot be periodic. So, and over here so we can see on the left, he had some more substitution rules where a kite can be substituted by two smaller kites and two dart halves. And then if you start off with this in the center with this kind of the sun pattern, and then you continue inside, you go inside further and further into like a fractal, you divide it and you continue like this, and you get this beautiful pattern. And again, once again, it is non-repeating because it's non-repeating. And this is something which this interesting shape, it was just discovered last year. So it is a tile, it is made by gluing 8 kites together. 8 so 60, 90, 120, 90 kites, those 4 angles, the kites are and together, and this creates once again an aperiodic tessellation. And this was just discovered last year. So this is a history of this aperiodic tessellations. Like we started in early 1960s. First mathematicians were very intrigued. They were very much intrigued by this problem, whether we can have such a thing as a aperiodic tiling. Initially, they thought it was impossible. And then they found a set of like 20,000 odd different tiles were discovered, and they could create an aperiodic tiling. And slowly that number reduced to like 100, and then down to 6, and then finally to 2 by Roger Penrose in 1970s. And then finally it stayed at 2 till last year, and when this tile was discovered by David Smith, and it's called Einstein. That is basically, it is yes, it's a 13-sided shape. Ein means one in German, and Stein means stone, and it's a very it's not that, yeah, but it apparently with this one tile you create an aperiodic tiling. The pattern never repeats. And in nature, we see that in hexagonal tessellations are in honeycombs, in bees shown on the right top. And then the snake skin is a tessellation like a rhombus kind of shape, like the bottom right. And these are all periodic, right? And then, so the people started wondering if aperiodic tiling pattern can ever occur naturally in nature. And Penrose himself thought it was very unlikely, but then it was found in aluminum manganese crystals, right? So till then, all crystals were considered to be periodic. Like for example, if you have your sodium chloride crystal, it is just sodium and chloride ions. They alternate on the vertex of a cube, right? And the pattern keeps repeating. But these are your aluminum manganese crystals. The pattern never repeats in these crystals, and they have a new name now. They're called quasi crystals, and they look very similar to Penrose tilings, his pentagon. We can see the 5-point, when if you look close, we can see the 5-point pattern in this. Yeah. Yeah, so there are a number of amazing, sites which explore tessellations, and so basically, math is filled with such fascinating topics like fractals and tessellations. And if we do some even little bit of all this to our kids, it opens up their imagination, and they know they won't find it a boring and a subject anymore. Yeah, that's what. Yeah, thank you.
All right, super.
Yeah.
Okay, we have some time. Cells in our body is tessellated. Yes. This I read somewhere, Bama, but cells in our body, what Lata is talking about.
Yeah.
There is a book by What is Life by Erwin Schrödinger, where he
Oh,
talks about tessellation and how it is actually aperiodic tessellation in the human body and different
okay.
organs and all that. Yeah, yeah.
Okay. Wow. Yeah. Oh, he talks about aperiod in nature, is it? That means,
Yes, yes,
yeah.
yes. So
Okay.
somewhere he
Okay.
talks about, I'm not sure whether he uses the exact word or the term aperiodic,
Okay.
but he does talk about it. I'll see if I can get a hold of it sometime.
Yeah,
Yes, Lata,
sure.
that is right. Any
Yeah.
other questions on tessellations? Do you think something like this can be taken to our classroom?
Yeah.
Okay. We'll come back to it. We'll come back to it. All right. So that is as far as tessellation is concerned. Now we will move to uh, a different topic. Hang on, there's somebody who's chatted. Can we ask kids to design their own tessellation? Absolutely, Lata.
Yes,
That's the
yes,
whole
yes.
idea.
Yes,
That is the whole
definitely.
idea.
Yes. So that little bit, that square which I showed, right, which you can cut one side and move it, with that itself, kids create very nice tessellations, very different ones. And it's like you give them as a homework or something to try it out at home. They do come up with very good ones, um, very different ones. Yeah.
Great. Okay. I hope you have some sheets of paper with you. Now, the next one is going to be more a practical session for the next 30 odd minutes, and then we'll take over from here. Sendar, if you're ready, we can.
Yeah, we need exactly 3 A4 sheets and a scale and a sketch or something like a marker. Maybe all of us can take a minute break to collect it if it's not available. So maybe in just a minute we can start.
Yeah. So if you have, so what we need is 3 A4 sheets, a sketch pen, and a scale. If you don't have it handy, please get up and collect it from nearby your place. We will start the session in about a minute. I'm just wondering what joy Roger Penrose would have got when he saw the aluminum tessellation look so much like the one he created.
Yeah. Yeah.
It must be seriously fascinating for him.
Yeah.
Oh, wow.
Just it's easier. Focus on that.
Okay, Sandar, we can probably start. By the time you intro, in case somebody has stepped out, they will join back.
Yeah. The tessellation is something which I really liked today more than anything else, I guess, because it was just fascinating and just bringing back children to the awareness that in 2022 something has been discovered is extreme motivation for many children to, oh, I'm going to make someone, I'm going to discover something out of it or something like that. And then you can get glued on to this kind of tessellation is just magical. It's like
Actually,
suddenly,
that slide, no, Sendil,
yeah.
3-4, I mean, eco sessions, it was not there. The
Yes,
last few, yeah, that is new. So this is,
Oh, it's just
this one
magical
is,
actually. Like,
yeah,
and the thing is, even this one or the other one, which is aperiodic, it it looked actually quite simple. It didn't,
yeah, it's very
yeah,
simple.
it is not so difficult also. And that's the when someone discovers something and it's quite simple, it's just
Yeah.
so much encouraging. It's just, it doesn't make me think like, oh, I need to be a rocket scientist to find this. It's like definitely it's a level playing thing.
Yeah.
Suddenly anybody in the class would feel like, oh, anybody could find this. But it's just that, have I really put my time and energy into it? And if you're ready to do that, and this is something, if children can get involved in math without a sense
So,
of time,
yeah.
that's the magical thing. Yeah.
So this person who's discovered this style, no, he's a retired printing technician. And
Wow.
yeah, he was not sure. He loved. He started blogging about these tessellations because he loved different shapes. And then when he found this out, he contacted a math professor. So and then they proved it together. Yeah.
Yeah, it's just amazing. Yeah.
Yeah.
Thanks for collecting all those things together. Yeah. Just fantastic. Yeah. So about this origami, this is something from a teacher called VSS Shastri, and this teacher is also someone who has been in a bank, and he retired from a bank, I think, and then Syndicate Bank or Canara Bank, something like that, and then. But he always had this fascination to math and make things simpler, and so these are a couple of ideas which came from him. So this is a general boat making, which you all take the A4 sheet and then make it into a square, which is regularly what we do. And if you're ready, just start doing it along with me. Yeah. And this
Whoever
boat
can
making,
keep the videos on, please keep it on. So that way we will know who are all, I mean, not we will know who are all working. I mean, it'll be fun to do it as a class exercise.
yeah, it will be really amazing to do it as a group. Yeah. So, but these are simple things which we tend to do during our school days in the monsoon, and the southwest monsoon is also just delayed, and we are having this showers in Tamil Nadu as of now, which should have come in August, but now it's delayed. But we are having it now. So keep this sheet also safe. That's also required. And we go on to the next one. So we have done this, and then we have cut the sheet, right? Square sheet is available. Ramesh, the next. Yeah, now we have cut this, and this is where we are ending up with. The next. Yeah, we fold this to make a square. So it's a square now. It's just, we start from here, we move to a half fold and then a double fold. Yeah. And now you sort of open it, you will see either 3 pockets, or it will be like this, right? So once you can see one pocket on this side, or the other side you can see one pocket. So it can be like that. So you fold one on one side and the other 3 on the other side. Yeah, the next. And now we see this like a small pocket, or like a hat, inverted hat. That's what we see on one side, and the other side you see these sheets. Yeah. There's a message.
Please repeat.
Okay, so from here we had this four folds, and we can just take one leaf of the 4 so that you can see something like a pouch, and fold that one leaf, and then all the other 3 goes to the other side, so that there is one thing like a pocket, and you hold that. You can just, from this triangle, you can just open the pocket, and slowly, if you keep pressing the pocket, you will end up having a rhombus kind of a square. Yeah. Yeah, the next one.
Does it work, Anupama? Okay, cool.
Yeah, and we sort of open that to make this. Once we got the boat, now you see the boat, and now you start unfolding everything. So we go back to the initial shapes. We slowly unfold them, so that now we are going to watch the creases. Now you see everything, and you see those creases. I can just make some of the creases darker. Choose to do. I'm not sure how much it will be very visible. Okay, fine. So you take any triangle from there, and I have just taken one triangle closer to this. And here you see many triangles, right? So you see about some are larger triangles and some are smaller triangles. So you see those things. And the next one, Anish. Yeah, this is how you see end up having that. And in that, we are just going to mark the squares of the sides of this triangle, which you can see. So all these triangles are of the same size. So that makes it, in a way, I'm not sure if it's visible. Is it visible?
It is.
Okay. So in that, you can end up marking as 1, 2, 3, and 4. But this 1, 2, 3, and 4 is pretty much of the same size, or exactly the same size as this 1, 2, 3, and 4 here. So that way, by using the boat making itself through origami, we can explain to children pretty easily this AB square plus BC square is same as AC square. So this is one exercise here, which is of course with a isosceles right triangle, but I'm not sure if there is a possibility of doing it with any other triangle. That can also be an option which we can try explore it ourselves, but this is pretty straightforward for us to experiment this. Yeah, move on to the next one. Yeah, now that leftover sheet for making that square. So with this sheet, you see this, it's just with the no folds now, it's just a long rectangular sheet. You just make it 1/2 fold. So there is a crease in the middle. So that's what we are doing. Just fold it once. Slowly we're doing it, making the crease clearly evident. Yeah. From here, you make another fold to make it into 4 divisions or 3 crease. Now we added 2 more crease, which is, so initially when we made 1 fold, we got 2 divisions. Now when we made another fold, which means like a double fold, we have 4 divisions from 2 folds actually. So this is the first fold, this is the second fold. From 2 folds, we could see 4 divisions. And we move on to make 8 folds. Another fold. We do it this way. This is the 3rd fold. We started with the first one was started from here, first fold, second fold, and then the 3rd fold. And in 3rd fold, we open it and then see 8 small rooms from that rectangular sheet. Now we can do one more. Can we? What's the next one? Yeah, we'll do one more. You can do any ways you want. So we end up seeing 8 rooms on top, 8 rooms on bottom. That's 16 we end up seeing from the 4th fold. This is the first fold. This is the second fold. This is the 3rd fold. This is the 4th fold. For 4th fold, we got 16 little rooms, 16 divisions. Yeah. So from this, there was one thing which there was a message, right? I couldn't follow. Yeah.
Yeah,
So
it says it's about fractions, is what Lata was saying.
it is almost like fractions, but it could be a little more. So the thing is, like, from there you could make another fold, say a fifth fold, and it's not fractions. Can we say it as fractions? Not so sure, but yeah. So from the fifth fold, we got 32 rooms, 32 divisions.
Yeah.
From the fifth fold.
No, we teach equivalent fractions in a similar ways in the you fold like half, then you show that half is nothing but 1/2. Then you make one more fold, then you have 2/4 is same as half. So you have, so this
That's
way we
definitely,
teach
yeah,
equivalent
that's also
fractions.
true. Yeah.
Yeah,
Because
that's all. Yeah,
because the shape is getting reduced, because the
yeah.
initial one is always a same rectangle.
Huh.
In that fashion, if this can be considered one fold, fractions could be like that. But fractions is like 30 to 30 seconds is same as 2 halves, or 4 quarters, or 8 1/16. So that way, yeah, it is very much related to fractions. But here's
Yeah,
a connection which we are trying to make between the number of folds and the number of divisions. That is
yeah.
something which we need to be which we need to bring the awareness to the children. Yeah.
Yeah.
Let's
Lata
Yeah,
has brought
that's
that
true.
out also,
That's true.
and
Yeah.
Suvarna Lalita also. They're talking about
Correct.
number of
Powers of
folds.
2. Yeah.
Yeah, powers of 2 or their exponent. Kanaka has also talked about exponent.
Correct.
Yeah.
Yeah. The next slide, we can see the explorations what we have done. So once we do this with children and then ask them how many folds did we do and how many divisions, and then we can ask them to estimate what is the number of divisions which is going to be when we do 6 folds, when we do 7 folds, what will be when we do 100 folds, what will be when we do n folds. And this way we can explore along with children what is the exponents and the powers of 2 and how does it increase and all those things. So far it's very sort of simple enough, but next one is really nice. So you move on and then see it is what happens when there are no folds at all. When there are no folds, it is just one whole thing with no divisions. It's just one division. We can say it as one block. Hence, 2 power 0 is 1 is a fantastic explanation actually. So it's 1 unit because no folds. Otherwise, explaining 2 power 0, something power 0 is very difficult. This way, anything power 0 is just 1 unit is a very interesting explanation if we continue to do this. Yeah.
Nice. Lata, does it hold good for any shape? Yes, preferably a rectangle. It could be a square, of course, I mean, which is a special case of a rectangle. But other shapes, it becomes difficult to exactly fold it. You have to look for the lines of symmetry and carefully fold it.
That's true. Yeah, we can make a tetrahedron with 2 A4 sheets. You can take a sheet, and with this sheet, you fold it into half on the longer side. One nice fold. And all of you have done this. And we can open it and then see other crease, center crease clearly. Now you can
Both sheets?
No, just one sheet. Actually,
Okay.
both sheets. You're right. You're right.
Okay.
Can we do both sheets? Yeah. Yeah, both sheets. 1 and 2 sheets.
Looks interesting. Yeah. I have my daughter in the background who's looking at me and saying, "What are you making? It's looking so interesting." That's a live demo of how students feel.
Yeah.
Yeah.
And you open them.
Yeah.
Open both sheets, and you're going to make.
Today is Mila's birthday.
That's true. Yeah.
Okay.
So you take this right top corner and you hold it in such a way that you're going to, this right top corner is going to touch the middle line. Yeah, middle crease. And it's going to be like this. Yeah. So it's going to be like this. So the same way I'm going to go to the other sheet also. Yeah, that's done. And so it looks like this for you, or something like this. Yeah. Now, if we fold it like this, yeah, the next one you can write. Yeah, this is what you end up having. And then you take the other one and fold it on this line itself. It doesn't quite look like a triangle, but a little tail is folded inside. So that's what happens with the, so there is this little piece inside. So you take that and you have that little piece inside.
Do I tuck the little piece in?
Yes, in the next one, we are just going to fold it inside. So you turn the other way and fold it outside there. Yeah. So that it just forms into a triangle. And when we do that, we end up having 2 triangles. But there are creases to explain, to help us for the next move. Yeah, now you have this one long thing. There is one crease which you see in the center on both things. So you can use any of the crease and then fold it in such a way that the top edge of this triangle will come and bisect the base. So you can fold it that way. And eventually, like you can fold all 3 sides in a way that it falls on one on top of the other. So you are just going to make those creases, that's all. Go inside also, as you said. Ramesh, it can go, the small tail can go inside, as you said. So that all 3 sides. So we have something like this. When we fold all 3 sides, it will end up something like this.
Yeah. Oh, there are messages. Sorry, I was busy doing it.
We need to make two like that, Sendil.
Yeah.
Okay.
Once we, yeah, I'm doing two things parallelly, but both of them with the same things, same steps.
Okay.
Now both of them look almost like a triangle or it's like a pyramid with like sides open. Yeah, a triangular pyramid which is open.
A tetrahedron.
Yeah, it's tetrahedron. Oh. And the next one. Yeah, so this is something which we have done. So folding all three sides. There's a smaller one which we have made. Now, once we have made these two, this is the time to connect them. Yeah, have you opened it and started connecting? So here, now the connecting is the key thing. So what
Sendil,
happened?
we are not able to see the video.
Okay, sure.
Now
So
it's okay. Yeah.
we see this triangle. So
Hmm.
there are two things, and you fold one inside. Just two are there. One is
Okay.
folded inside, and then two are visible now. So,
Yeah.
which is what you see in the right hand side bottom one. You see that? How it is folded? So you bring both of them with one folded inside. Okay. One folded. It's like this. Both of them is only one is folded as a base, and then two are open. Okay. And the next one, next slide. You see where it's getting inserted. Yeah. So you see both like a triangle like this. Okay. You see both like this kind of triangles. And now you're going to lock these two and then get this third shape. So it's here and in these two pockets, if you just allow them to, you find two pockets here on these two openings, and that's where these two flaps are going to go inside. Like this. Yeah. I can just remove it like this. Yeah. But the key thing is like to fold this one. So once you fold off the three sides, once you fold two just one side on both things, then you have these two. In this, in one of the triangles, you should have two pockets. Both you will have two pockets. You just start inserting these two things into one into this first, and then the other one here. It
Yeah.
just goes and fits.
Mm.
Yeah.
Yeah, it's very nice.
I'm getting a pyramid here actually.
Yes, that is the one. Exactly, Lata.
Yeah.
Oh, you got a four-sided. Oh,
Yeah, four-sided is when we don't fold any three sides. Any side, if you're not folding, you could probably get a pyramid, but it won't be locked actually. Is it locked fully?
Yes,
Yeah,
it
mine
was.
is also
As
locked.
you said, I folded,
Is it a
and I just
square
inserted
base?
one into it.
Yeah, there is a possibility of a square base, but this tetrahedron is something when with a triangular base always is something it's becoming very solid and it can just stay for a good time as well. So, but the square one, the square base is something not so easy because it fits on a different level, I guess. So, yeah, when I was doing, I also got a square thing, but since tetrahedron is something which we were aiming at, I just stayed with tetrahedron. Yeah.
yeah.
Okay.
But if you insert it in the pockets, Lata, it kind of comes, I think
Yeah, it comes very quickly.
kind of comes like this.
What else other than the tetrahedron?
Lata got something which is like a square pyramid.
Square base, square pyramid.
Square base pyramid, but the bottom of the square is not filled.
Yeah, it's not fit.
Lata, can you show that?
Yeah, sure. I just inserted these two. To form like this.
See?
Yeah.
Yeah.
Oh,
Interesting.
okay. Okay, okay.
Yeah.
Yeah, this is what I also.
And is it
tried
porous
something
at the
like this.
bottom? Does it have a hole at the bottom? Can it be
Yeah.
used as a No, I'm
That
just
is
wondering
nice.
whether we can use it as a container.
Yes.
Right. Okay. Very nice.
Yeah, I was also thinking about something like that. Yeah, it came something like this. Yeah. Yeah, like a pyramid, but it was
Right.
not just steady enough. Yeah.
Right.
Because the bottom, it is becoming like this. It's
So
just not a complete bottom. It's like little covered. If I just put it like this, like a container, as you said, it can be, but it's not, it's sort of flexible and it's moving like a rhombus, like an elastic rhombus,
yeah.
but it ends up almost like a pyramid. Yeah.
Okay.
Yeah, but if we just fold one inside and then get this, then it ends up as a, yeah.
Awesome. Great.
Yeah.
We have one more exercise.
Yeah, one last.
Yes, yes.
And yeah, again, we make the square shape from this A4. We fold this one and then we cut it. Yeah, once we have that, now you fold it to half. The square, so it can go on any side because it's a square. Once we have that, so again, from here, you can start making this corner and so you bring the right corner again, like the same shape itself for what we have done the tetrahedron. So Yeah. And the other side, we are going to take this and keep it here. It will look like as if we are making a rocket. Yeah. So we have done this fold and then this fold. Yeah. And the next. Yes. And we fold this.
By the time it finishes,
Yeah, once we do this and then you open up, you see some things like there is one cross line also like this. And then these are the things which we see. This line and then I'm just darkening the crease itself. So once we do that, yeah. And the next line. So this is what you have. You have these 1, 2, 3, 4, 5 rays which are going from this corner or the left hand bottom corner, and there is one diagonal which we have drawn. So now we know that this diagonal here, it's 45 degrees because of half of the right angle. This is 45 degrees. And so this one is going to be just 15 degrees. No?
Yeah.
Yeah, this is 15. So they know what is this one. That's 45 and this 15, 60. So this is 120 degrees. If this is 120, this becomes 60. And so we can slowly mark all the things.
Right.
So you end up having the different angles. The next slide, we can see it just increases. Like we can play with the triangles with the children so that the sum of the angles, so 45 degrees, 15 degrees, the next would be incrementally, it's going to be like again 30 degrees and then 45 degrees and then 60 degrees and 75 degrees in this left hand corner. So that also children can see. The 45 degrees really help us to identify these things. Yeah. So when we play with the or introduce angles in grade 6, some of the activities what we have done can be done between sometimes grade 5 also, when we introduce formal geometry. So when children get to know the terminologies like acute angle and isosceles triangle and all these things, it'll be nice for them to not get loaded with these terminologies, but to experience these terminologies along with something hands-on, so that they are glued into it and then they want to enjoy the whole process. Yeah, as we progress to the next slide, we can see the other angles as well when we keep marking. Yeah, so it's from 45, it becomes 60, 75, and then 90 degrees is that middle, because the diagonals bisect at 90, and then 105, 120. So here also in the left corner, we can always see that from 15, it also increases to 30, 45, 60, 75, like that. And all these explorations after we do something in the class is always nice. Now we come back to, because of both the other things, we have finished a boat and then we have seen a shape, and the other one also we have done a tetrahedron. But now we're not so sure, like we have mentioned it as a bird, but it is not yet a bird. So we go back to our fun thing from our learning. So this is how it was when we had this fold.
You can actually see the bisectors there in the
Yeah,
previous
Yes,
slide.
yes,
we
yeah,
can,
yeah.
So we did this.
So the one line bisects the other triangle, and that other
Yes.
triangle is also bisected by another line. So you can go on see the gradation of the triangles and the bisectors there.
That's true. Yeah. So you go back to this folded shape, and from there we can see it's almost like a, if we could imagine it as a peacock, it's almost like a peacock standing with a in a tree with a tail facing down. So now you can give a shift or a neck, a slight turn or something like that, so it becomes easier. So once we do this, then you go to this fold and do this one. Yeah, do this fold. And however you want to see, wherever it's sitting and however it's facing. So it could be any ways it can be. So it can be like this, and then here is something which you can make it for a yeah, it can be like this. It can end up like this.
So nice, no?
Yeah.
It's a peacock.
Yeah, it can
Should be a blue jay too.
Maybe a
yeah,
blue
it
jay.
can be anything. Yeah.
Or it could be a lovebird.
Yeah.
And it could be a
Yeah, it could be like this. Yeah. You can have the shift any ways you like, and you can have all these different shapes that we made. Yeah.
Can you make a Rottweiler out of paper?
Yeah, it's so
Okay.
much fun with paper.
It's to have
Very, very fascinating. Thank you. Now we have Ruchi. Ruchi, you're there?
Yes, I think Ruchi has joined in. Ruchi, can you hear us?
Good evening, everyone. I'm here.
Yes, Ruchi.
Thank you for joining, Ruchi.
So we'll take you to the case study, which
Thank you so much, ma'am.
yeah.
Thank you so much, sir.
No, not at all. Thank you, Rakesh. Now today is like really fascinating because one is hands-on, the other one, the aperiodic, completely spooks you. Like Senthil said, it's so simple yet something so amazing as a discovery. Yeah.
Sir, actually, sir, I have some other ideas. I
Yes.
will describe maybe in the next meeting.
Yes, please,
Very-
please put it down. We will take it up at the beginning of the session. So today we
Yes,
are
sir.
scheduled for Ruchi. Ruchi, if you want to go ahead. So you had talked about, we had asked two questions in the end of last session. One of them was, if you take any topic in class, how do we introduce and develop a certain topic? I mean, today we saw in the hands-on origami, a way to introduce exponents, for instance, or a way to intuitively flow with various angles of a certain, a bird which we were making and so on. So the question was, if you take any topic and can you describe how you will introduce a topic of that nature, Ruchi? That was the question. You want to go ahead and explain what is that you have written?
Okay, sir, I will prepare myself for representing that topic.
Yes, Rakesh, thank you, Rakesh. So you can present it. I was asking Ruchi, Rakesh. Yeah.
Okay, sir. Thank you.
So basically, here by introducing my topic of algebra, and we move to the formula derivation. Like we talk about the role of pi, how we calculate 5 and the area of the rectangle, and then again the area of the surface area of in fact of 3D figures that to be categorized in terms of prism and pyramid. Okay, basically I just skipped off of the context what I was dealing. जो अभी मुझे याद है, according to me, it's when I was dealing with algebra in my class. Actually, I was teaching my DLA trainees of about the algebra, and I started with those examples of ice cream sticks. We were creating patterns, and I asked them to generalize the formula.
Okay.
So it is written train, it is trainee. I was dealing with algebra, and to an extent we moved with the formula derivation. So there was the formation of U. For L, it is the same, but when we shifted to U, that there was a two ways of representation, and they came up by themselves with the two different variations. Of course, when we simplify them, the answer will be the same, of course. And similarly, we started it with, rather than going or talking about algebra, what is algebra, we simply started with making patterns of sticks by drawing them, that if you have to make one L, how many sticks you need. If you have to make 4 Ls, then how many sticks you need. And if you are continuing with this pattern up to 5 and 10, then how many. Okay, if we go for n numbers, then how many sticks. So they were very easily able to find out the relationship between the number of sticks required to make L and the number of sticks initially required for a 1 L. Similarly, I went up with the use.
Go on, Ruchi. Oops, I unmute. Can others hear Ruchi?
No, I think we cannot hear our audio. Ruchi, can you hear us? We cannot hear you. Ruchi, we cannot hear you.
Okay, I think the part she was talking about is, let's say, making patterns. It could be making patterns like and continuing to extend those patterns. So let's say we make a pattern which is like, okay, let me see if I can get a pen.
Actually, ice cream sticks are easily available for
Yeah.
students also and for us also. So we went up with the ice cream stick patterns initially. So after L, we shift to U, then how you will go with the U. Then we derive the formula for U. Then for M also they tried. So this is how I went up with the topic of algebra. Similarly, when I was discussing with them the concept of 2D and 3D, I simply started with the concept of prisms and pyramids, and again their nets we talked about, how when we open it, how it seems to be, how a prism is rather than using the word how prism is different from a pyramid, I simply asked how this cube is different from cylinder or a cube is different from a cone. Then we had the reflection about it, that in cone the surface is reducing to a point, whereas in a cylinder from top to bottom the surface at every point is same, till the height it is reaching, the area is almost the same, it is going on with, it is not reducing to a point. So they were able to analyze these things, and then we share first they had a talk between themselves, and then they shared it with me in a larger group, that what they analyzed. And after this we created the nets of certain things like cuboid, and then of course cylinder, and then cone also. In cone they really have to go with some of the problem solvings they went up, but I didn't give them you draw like this or this. I said you just try out by yourself and sort it out how you will create a cone. And then again the relationship between cone and a cylinder, which we usually talk about, I ask them to drive that also. So here basically rather than going with the concept, I say ki, in a abstract form or in the very much technical terms, it's always good to trigger the thinking process of the learner, whosoever it is and whatsoever the stage is. That thinking process actually makes the learner to understand what I want to communicate, because he is struggling at that time and he just tries to pick what where I want to scaffold that. And I also, rather than giving the whole information, try to connect at that point where he is actually struggling or she is actually struggling.
Got it. Got it. Wonderful. Thank you, Ruchi. There was one more question we had raised last time. Sandal, you want to take that? Sandal?
Yeah.
Yeah.
So can you hear? Yeah.
Yeah. Yeah.
So this is something which we have experimented last week when we talked about, and then the question was, it's on this thing, how many sides we see, and then it's 12 centimeters on the base, and if the slope side is the edge, if it is root 136, and what is the other sides? Like what is the and what is the volume of this is the question basically. And once we find the volume, and how do we approach and find the volume, and once we find the volume, what can be here it ends up as the surface area and the volume are similar. Like what could be other shapes which can be of the similar values? So this is one of the interesting things.
Yeah. Yeah. Ruchi has said same can happen in case of a cone as well as a sphere. If sphere has a radius of 3 units, I think is what she means.
Yes.
Which is right, because 4 by 3 pi r cubed, so the 3 units will become equal to the 4 pi r squared. Yeah. And in cone, is there any specific way in which it has to happen?
Yeah, there is definitely some way to it. I think it is not for any cone for sure. And the cone has to be in such a way, the height is also very similar, right? And so the height should be lesser than the radius, I think. When I say the height, the slant height should be lesser than the radius. That's when it works. That's what happens here also in this square.
Yeah. Even for a cube of side 6, it will work, I think.
Yes, that should be true. Yeah.
Actually, it's quite interesting. Then, so it's a matter of just, it can actually be a place where geometry and algebra sort of meets also.
Yeah,
because
and it very well plays into the low floor, high ceiling, as you mentioned. It just really pushes children to the next level. Yeah.
Correct. Because the surface area of a cube is 6a squared. You equate that to a cubed, a drops out as 6. So that way you can keep it.
That is true.
All right. Superb. Thank you, everyone. Yeah.
Thanks.
And,
it was a wonderful session. I think if a math session was this creative, kids would look forward to math classes. So please, everyone share your feedback. I've put the link. And thank you, Ramesh, Bama ma'am, and Senthil sir. An amazing session as usual.
Yeah.
Thank you.
Yeah. Thanks, Bama. Thanks, Senthil and Smita. Thank you very much. And
thank you.
Yeah. Thanks a lot. Thank you, folks. Bye-bye. Bye-bye. And Priya, my daughter, wants to convey a happy birthday to Nila. So I want to put it officially when it's still getting recorded. She's been telling me